All right. So good morning, everyone. Um, so what I'm gonna do now is present the following paper that we've written together with Professor Mercorelli, with the title of Parameters Estimation of a Lotka-Volterra Model in an Application for Market of Graphics Processing Units or GPUs. We would like to begin with a bit of a background, answering the question why we decided to conduct this research. Um, so over the last several years, the market for GPUs has seen a substantial increase in demand. Initially, we saw enthusiasm from gamers willing to get better and better performance out of their GPUs. And during this period, the demand for graphics cards was steady with some minor fluctuations. However, since the introduction of the blockchain and cryptocurrencies, people were eager to begin the mining operations. Eventually, as the process became more computationally heavy, miners were switching to GPUs and the market started to change significantly. So looking at the charts showing both the price of Bitcoin and the shipment for desktop GPUs on the bottom, we see clear correlations. Whenever the price of the digital coin increased, so did the demand for GPUs, which is clearly visible in the run during the last quarter of 2017, but not so much in 2021. And since there are several competing firms that produce these GPUs, we asked ourselves, can we use historical data with market share for each firm, namely Intel, AMD, and NVIDIA, or XYZ, as we denote them in the equations, to model the interaction between these competing firms? We also attempt to model how the future of the GPU market would look like. So first of all, we will start with the overview of the Lotka-Volterra model. After, we will explain the steps that we have taken during the whole process, what methods we've used in order to find the parameters and the model data for future projections. Then we will explain the results that we found, and finally, the limitations of the study. All right, so the model. When we consider populations as the subject of research, it's very likely that we will come across the term population dynamics, which already implies that we are dealing with something that's constantly in motion. And in order to visualize and model population dynamics, the Lotka-Volterra equations have proven to be a very useful tool. These equations generally describe the changes in population sizes of at least two species that are interacting with each other. And the most famous version of the model is the predator-prey relationship between two species, like bears as predator and fish as prey. The Lotka-Volterra model is also used in all fields of modeling where competition is present. And also in economics, it is possible to apply this model. The equations below is how the general Lotka-Volterra model describing the population dynamics of two species looks like. Here, X represents the number of prey and Y represents the number of predators. On the left side of the equation, dx over dt and dy over dt represent the growth rates of the populations based on the changes within the population sizes over time, which is denoted by letter t. The Greek letters alpha, beta, delta, and gamma on the right side of the equation are positive real parameters that describe how two populations interact with each other. The first equation represents the dynamics of the prey population. It is calculated by subtracting the rate of predation from the population's intrinsic growth rate. And since it is assumed that the prey has unlimited food supply, theoretically, its population can grow exponentially if the population of predators and the rate of predation are equal to 0. In the second equation, we have the description of the dynamics of the predator population. It is calculated by the rate at which it consumes the prey minus the intrinsic death rate. Since the growth rate of the predator population does not necessarily equal the rate of predation, it is expressed by delta xy, and in this equation, gamma y denotes the loss rate of the predator population due to natural death or emigration. This results in an exponential decay of the predator population if there is no prey available to be consumed. Now we will move to the method part. So while there is limited research where the Lotka-Volterra model is applied for more than 2 species, we have found an example that describes the relationship of 3 competing firms in the mobile telephone industry. In their paper, Kloppers and Grief used historical data and applied the integral method followed by ordinary least squares to estimate the unknown parameters. Inspired by the example, we have formulated the general equations for our case of GPUs. Here, X, Y, Z represent the market share of each competing firm, and ABC are coefficients that we need to find. And to estimate the parameter values or the coefficients, the integral method described by Kloppers and Grief was used. Simply put, the calculation is done by integrating both sides of the equations with respect to t, and as the next step, we have applied the trapezoidal rule to come to the equations as you see on the slide. Then, given that we have the historical data that we've collected for each firm market share, we can represent the set of equations from the previous slide in the matrix form. And it is important to mention that we are showing the calculation only for the first firm, and exactly the same procedure is done to the rest, the firms Y and Z. In this matrix, D is the difference of the market share from one period to another, and the matrix X contains consecutive pairwise means presented here. And meanwhile, the vector A contains the unknown parameters. We've used a least squares method to find the vector values using the following formula. Transpose matrix X times the metric itself to the power of -1 times, again, the transposed matrix times D. Now we will present the results of our calculations. Applying the proposed integral method, the resulting system looks like this. First of all, it's important to mention that before conducting this research, we had no idea what firm is the prey and what is the predator. Unlike the classical application of the Lotka-Volterra model, where it is obvious that fish is prey and bear is the predator, it was not so clear in our case. Therefore, only after we've used the historical data, we were able to say what firm is the predator. And it turned out that the second firm, the firm Y, which is AMD, is the predator. We see that the coefficient is negative if we look at the first coefficient in the second formula, negative 0.12, which is a sign of the predator species. Interestingly, the share of the first firm increases by the actions of the predator firm with coefficient of plus 0.17, while the third firm has a negative influence on the growth rate of the first firm, which is shown by coefficient of negative 0.34. Looking at the second equation, which is our predator, we can see that the first firm is not acting as the primary source of the growth, and it turns out that the third firm, is the main source of the predator share growth, as seen by a large coefficient of 0.93. Looking at the third equation, it is confirmed by the coefficient of negative 0.54 that the growth of the firm Y, or the second one, comes from the decline in the third firm, which is NVIDIA. Given that we are dealing with competing firms, predator and prey, we were curious at what point do we reach a point of equilibrium? How do we achieve and maintain sustainable levels for all three firms, a point where the population of each species remains unchanged, or when dx over dt is equal to 0? In order to estimate the equilibrium point for each firm, each equation in that same system of equations was set equal to 0. The obvious solution for all equations is when x, y, z are all equal to 0. And another solution was found at points of x equals 0.63, y equals 0.11, and z equals 0.17. In order to get the values for the model data, we have used the Euler method. The following figures represent the observed data and the results of modeling. As we can see by the results, the model fits well to historical data of the first firm, Intel, which with r squared equal to 0.78. The forecast on the right shows that the stable state is reached at 0.63, which corresponds to the previously calculated point of equilibrium using another method. As for AMD, the second firm, the predator, we see that the model does not fit the observed data well, which is confirmed by the r squared value of negative 0.99. Such a high negative value implies that the found best fit line fits worse than a horizontal line drawn through the mean of all y values. This can happen if the regression line does not follow the trend of the observed data. However, if we look on the left, the forecasted data does display a similar trend as the observed data. And nonetheless, the future forecast suggests that AMD would lose half of its market share in the near term and will remain at an equilibrium point of 0.11. However, as the model did not fit well to the observed data, it is impossible to suggest the validity of the forecast. Finally, the model for the third firm, NVIDIA, shows a good fit with r squared value equal to 0.78 with an equilibrium point of 0.17. The forecast shows that the firm would lose some of its market share, but only by a few percentage points. Then we move to the limitations of the study. So overall, the r squared values show decent model fit for the first and third firms, while not being the best fit for the second, which is the predator firm. It's likely that either more data is needed to build a better model, or some adjustments to the methods that we used are needed. We've also oversimplified the model since we take into consideration only the historical data for the market share for each firm, and we ignore many other factors. Past performance is not a guarantee for future results, meaning we have to take these findings with a grain of salt. Nevertheless, the results indicate that the Lotka-Volterra model can be applied to investigate the competition of more than two firms in the market of GPUs or any other market where firms are competing for similar resources and customers. This is the end of the presentation. Thank you for your attention, and we're looking forward to questions and your feedback. Thank you.
Do you have some real data to check here? So how much of this is done on real data?
We have basically taken only the real data. We found the data from 2007 up until 2021, and each point of data represents one quarter. And we've done it for three firms. So basically we have these firms, Intel, AMD, and NVIDIA. And for each of them, we have the percentage of the market share that they have when it comes to shipment of desktop GPUs. So it was all done with real data.
Yeah, and you don't need neural networks to do this. Yeah.
Oh yeah, no need. We can use
old good mathematics works sometimes. Thank you very much. This closes the